Alright, so now we're ready to talk about coefficient restitution for central impact problems. This one's a little more complicated than the coefficient restitution problem where we just had one object moving. Now we have both objects moving, but everything's constrained to move along a straight line. So at the beginning, let's suppose we have two masses. I call them M1 and M2. They're both moving along this straight line. Mass 1 has a velocity v1i initially. Mass 2 has a velocity v2i in the i-hat direction initially. And of course we have v1i bigger than v2i, so that we know that block number 1 catches up to puck number 2. They actually collide with each other. And then we call ti the time at which they first touch. Okay, when they first touch, they have these two velocities. We got those two masses there, and we want to study that impact. So those two masses come together, they collide, and just like the softball in part 1 of the coefficient restitution video, we assume that these two objects deform, they get squashed against each other, and I define t0, the time at which they're at their maximum deformation. At their maximum deformation, remember the softball came to a momentary stop. When we get the two objects at t0, these two objects at the maximum deformation, they all of a sudden match their speed exactly. The two objects have the exact same speed. I call that v0, v0 on the I for both of these things. Okay, so between ti and t0, remember we have a special name for that. That's when the objects are deforming. That's, if you think of them as springs, that's when they're compressing. And in this time interval we call the deformation phase. Like so. Now after t0, that's when the spring starts recoiling. That's where these two objects start pushing out against each other, and they start regaining their original shape. And between these two phases, that's what I call the restitution phase, if you recall. And then finally at time I call tf, that's when these two objects are just about to separate. As they're separating, they'll have different velocities. And in this case, v2f is going to be bigger than v1f, and you can guess why. That's because v2 is going to shoot off faster than v1 is, so they don't pass through each other, right? So there's the basic idea. I've laid out the phases of this impact, the phases of this collision. Alright, so the next thing I'm going to do is apply the impulse momentum principle to this problem. And again, just like in part 1, I'm going to split it up into, just look at the deformation phase, and then I'll just look at the restitution phase. So now I have two objects in which to do the impulse momentum principle on. So let me just start at the very beginning. So let me start with object number 1. And here we have the initial momentum of puck number 1 is m1 v1i. Again, we're filtering out just stuff in the i-hat direction. And now what I have to do is add the impulse to the force of impact. So as they're touching each other, as they're coming in contact with each other, the blue puck, or puck number 2 here, is feeling a force to the right. Puck number 1 is feeling a force to the left, right? But the idea is clear, I think. So puck number 1, or object number 1, is feeling that force in the negative I direction. So therefore, its impulse will have a minus integral of f from ti to t0. And this has to equal the momentum of the system at time t0. So I've got mv0. And this is an important equation, so I'm going to call it equation number 1. Now we can do the similar thing for object number 2. And again, we'll look at it in the i-hat direction. So this gives me m2 v2i. There's my initial momentum. And now I add in the impulse, right? This one gets me an impulse in the positive i-hat direction equal to f dt. Integrate from ti, t0. And this has to equal m2 v0. The first one was m1 v0. Again, this time my initial momentum is m2 v2i, and here I add in the impulse because the impulse, the puck number 1, is pushing puck number 2 to the right, so which is in the positive i-hat direction. So now I add in the integral from ti to t0 f dt, and this has to equal m2. This is the momentum of object number 2 at time 0, so m2 v0. Again, this is an important equation, so I'm going to call it equation number 2. So the next thing I'm going to do is write the impulse momentum relationship for the restitution phase, when these two objects are separating from each other, when they're springing back to their original shapes and pushing themselves away from each other. And just so that I have more room to write some stuff, let me just move my impulse momentum for the deformation phase up at the top, and then I'll do the restitution phase right beneath it. In this case, for object number 1, again, we start off with an initial momentum, m1 v0. There's my initial momentum for the restitution phase. It's the same as the final momentum for the deformation phase. And again, this block is being pushed backwards to the left, so I subtract off the integral f dt. This time I'm integrating from t0 to tf. This has to give me the momentum at the end of the time period, which is m1 v1f. And then for the second object, it's really just the same story. Initial momentum plus an impulse. This time it's the impulse to the right. Gives me a final momentum. That is a momentum at tf. And once again, these are equations I'm going to use again over and over again. So I'm going to call this one equation number 3. And the one for object number 2, I'll call that equation number 4. So now we're at the stage of this derivation where we're going to do a whole bunch of messy manipulation. We're going to jostle terms around, combine some things, and it's probably not going to make a whole lot of sense of why we're doing what we're doing. But I urge you to just follow me, make sure everything that I'm doing makes sense, and then finally we'll get to some destination where cool things happen, and you won't see it coming, but you can at least go back and see the steps and make sense of how we got to where we're going to finally end up. So what I'm going to do is in my manipulations, I'm going to focus on object number 1 first, and then I'm going to go to object number 2. So if I grab equations number 1 and number 3, these are the deformation impulse momentum equation for block number 1, and the restitution equation for the same block, then what do we get? Let me just manipulate these terms a little bit. If I pull out this term, which is just the impulse here, the integral of f dt, ti to tf, and then put that on one side of the equation, everything else on the other side of the equation, then this becomes m1 times what? v1i minus v0, right? And similarly, if I want to do the same thing for equation number 3 with the restitution impulse here, we get the integral from t0 to tf, f dt. This is going to equal to m1 v0 minus v1f. And again, this first blue equation here, this one comes from equation number 1, and this one comes from equation number 3 above. Now what I want to do is I want to go back to my definition of a coefficient of restitution. Remember what that is? It's a ratio, right? We got the restitution impulse in the numerator, so this is the integral from t0 to tf of f dt divided by the deformation impulse. So here I'm integrating from ti to t0 of f with respect to time. So that's which one? And the numerator, I got t0 to tf. That's this one right here. So this is equal to m1 v0 minus v1f. And in the denominator, we have the deformation impulse, which is this one right here. So we get m1 v1i minus v0. And of course, these masses cancel out. Therefore, we can write this coefficient of restitution as a ratio of just velocities here. v0 minus v1f in the numerator, v1i minus v0 in the denominator. And there you have it. We've got the coefficient of restitution as a ratio of bona fide ratio of velocities, right? Or differences of velocity. But there's one problem with this formulation, and maybe you can see it here. Notice in my ratio of velocities, I have the v0 in the numerator and in the denominator. What's v0? Do you remember? It's the speed of those two objects when they're at that maximum deformation. At that one moment, these two objects are moving with the exact same speed. That's v0. But I can't measure that. Remember my bouncing ball experiment where I can just maybe measure a velocity of a ball just before impact, measure velocity just after impact, but it's going to be really hard to measure this thing in the middle of an impact. I have to measure that velocity at exactly the right time. A little too early, a little too late, I get a wrong velocity. So what I'm saying is I don't like this v0 in my expression. I would like to eliminate it somehow. So what I've done here in this last equation is I've sort of multiplied this. I've multiplied both sides of the equation by this denominator here. And therefore, that's what I get. And this one's going to be real important to me. What number equation am I on? I think I'm on equation number 5. So let's call this one 5. Now for object number 2, we're going to do the exact same thing. I mean exact same thing. We get the equations 2 and 4 that were the impulse momentum equations for deformation and restitution respectively. This time I'm going to not show every detail of every step. And once again, we get the coefficient of restitution as a ratio of linear impulses. There's my linear impulses again. So therefore we can write the coefficient of restitution as a ratio of masses and velocities. Of course, the masses cancel out, and we're just left with a ratio of velocity, or rather a ratio of differences of velocity. And again, I can write this expression just a little bit different, so I have no denominators anywhere. This one's so special that I'm going to call this equation number 6. I think that's what we're up to. And now I'm really in the home stretch. I'm almost there. So after all the work we've done so far, we've gotten equations 5 and 6, which I'm bringing together right now. Remember, 5 came from impulse momentum principle applied to block number 1 and doing a fair amount of manipulation. 6 comes from a whole bunch of manipulation of that impulse momentum for block number 2. And remember, where do we want to go with this thing? We don't like the v-zeros in there because those are hard to measure. It's much easier to measure a velocity before impact or a velocity after impact. But check this out. These two equations have the v0, the thing we don't like, in sort of opposite ways, right? I got an e times a minus v0 over there. I've got e times a plus v0 below it. Oh, notice I got a v0 on top over on the right side and a v0 on the bottom on the right side as well, and they're both opposite of each other. So maybe you can see what I'm going to do. So I'm going to take these two equations, since they have parts that need to cancel each other out, I'm going to add these two equations directly to each other. And in doing so, what do I get? This v0 is going to cancel with that v0, which will leave me with e times looks like v1i minus v2i. Interesting. And this has to equal, again, this is going to cancel with that. How about v2f minus v1f? Yeah? Huh. Notice I don't have any v0s anymore in my expression, and therefore I got something really cool. If I solve for e, my coefficient of restitution, I get e equals v2f minus v1f, and then in the denominator I have v1i minus v2i. So therefore I've got my coefficient of restitution as a ratio of the differences of velocities, but the cool thing now is I have velocities that are relatively easy to measure. I don't have that v0 in there anymore. Ooh, check that out. And furthermore, I want you to think about what v2f minus v1f means, and similarly what v1i minus v2i means. We'll go to the top first, v2f minus v1f. First of all, you'll remember from way back a while ago that this v2f has to be bigger than the v1f, right? Otherwise, they'd pass through each other, and that's not good. So v2 has to be sent off to the right at a faster rate than v1f is moving, if it's moving to the right. So what does that mean? That means, first of all, it means the numerator is positive, right? If v2f is bigger than v1f, boom, the top is a positive number. That's kind of cool. And in particular, if you think about it, v2f minus v1f, that's the rate at which these two objects are separating from each other. So what we have here, just like we had for the single ball, this right here is a rate of separation. In other words, if you're sitting on v1f and looking at v2f, the rate at which v2f appears to be moving away from you is this difference right here. Cool. And if you look at the bottom one, v1i minus v2i, what I say about v1i and v2i? v1i is the bigger one. So therefore the bottom here, the denominator, is also a positive number. I got a positive number divided by a positive number, so e is going to be a positive number. And if you think about it, this difference means the rate of approach of the two objects. So once again, just looking back at this, fresh eyes, once again we can write this coefficient of restitution, even though it's a ratio of impulses, we can write it as a ratio of velocities, or rather a difference of velocity. And just as before, the numerator, this difference of velocities, it's a rate of separation. And just as before, the denominator, it's a difference of velocity, it's a rate of approach. I personally don't like to try to memorize v2f minus v1f divided by v1i, whatever. It's hard for me to memorize that, but it's really easy for me to memorize rate of separation divided by rate of approach. That's the way we can think of a coefficient of restitution. Now going back to this central impact problem, now we've got a problem I think we can solve. Remember, originally we had a conservation of momentum principle. In other words, if we do impulse momentum principle on this system as a whole, we get m1 v1i plus m2 v2i. There's my momentum of the system in the i-hat direction before impact. And then we get m1 v1f plus m2 v2f as the momentum of the system after impact. And because these forces of impact are internal, I get this momentum, initial momentum, equal to the final momentum, right? And remember, that gave us one equation for two unknowns, the velocities after impact, assuming that we know the masses and we know the initial velocities, right? We had two unknowns for just one equation. But if also I know the coefficient of restitution, then I have a second equation involving these four velocities right here, in particular the velocities that are unknown, this one and this one right here. So I've still have two unknown quantities, the v1f and the v2f, but now I have two equations. So with these two equations, they're linear equations, I could, hopefully will, find the final velocities in terms of the initial velocities, the masses of the two objects, and this coefficient of restitution. And that takes me to where I want it to go. Over and out.